In this second question, explain the meaning of the term enthalpy change of formation. You will notice that they don't mention standard here, so you don't get 1 mark for standard conditions because they do not mention standard here. Sometimes they will say explain the meaning of the term standard enthalpy change of formation, but if you already remember the definition, if you say understand the conditions, I don't think they'll penalize you. You just don't get the extra mark or extra credit awarded for it. Okay, so what can we say? Enthalpy change of formation is definitely enthalpy change. So it is not the process. Be very careful. A lot of students say, oh, it's when 1 mole of blah, blah, blah. But this is enthalpy change. It is not a process. It's the enthalpy change for the process. So always be careful with your use of words instead of jumping in straight away. So it's the enthalpy change when you form 1 mole of a substance. So when 1 mole of a substance is formed, from its elements, it has to be formed from its elements, and everything must be in their standard state. Everything, including the reactants, including the substance you are forming, must be in their standard states. And sometimes the definition will say define standard enthalpy change of formation. So usually you will say under standard conditions. Seems a bit repetitive, but when you have a 3 marks definition, you probably get 1 more marks for the standard conditions, which will be 298 Kelvin or 25 degrees Celsius and 1 atm pressure. So I've simply included the standard condition here, even when they don't ask for the standard, because we don't know when they will give you 3 marks and when they will ask for the standard enthalpy change of formation. So it's good to always remember the standard conditions, but even if you write it down here, they don't ask for it, you just don't get additional credit. I suppose the 2 marks are from here, 1 mole of substance from its element, and the other one, everything in standard states there. Now next one, give the equation for the reaction. So you want the standard enthalpy change of formation of liquid sulfur trioxide. Be very careful, liquid. That's what they say, liquid. When you are asked to do enthalpy change of formation, always write the product first because of the definition, 1 mole of this substance. This is the state that you want. So now you're forming from the element. So sulfur as an element, and then you will have sulfur as a yellow solid, and then you have oxygen gas. And then you will have 3/2 oxygen gas because you only want 3 oxygen atoms, and oxygen exists as a molecule, they don't exist as an atom. So the elemental form of oxygen from its element as oxygen. If you decide to use S8, because sulfur can exist as a molecular form, which is S8, if you use that, then you will need 1/8 of that, so that you get 1 sulfur, so that you are forming just 1 mole of this SO3. Okay, and includes that symbols, so you have to have the correct stat symbols, including this one must be liquid, cannot be gas because of what the question specified. This next question, it says use bond energies from the data booklet. Well, now that you have the 2022 syllabus where the data booklet is no longer a separate entity, but rather it is included in the data booklet, so things will have changed. They might have provided you with the bond energy here. So if we are given the bond energy, everything is in the gaseous state, we can use delta HR equal to the total energy for bond breaking minus the total energy for bond forming. So it must be the total energy for bond breaking minus the total energy for bond forming. So what are we breaking here? We are breaking a nitrogen-nitrogen triple bond. So we have 1 times 944 for the nitrogen-nitrogen triple bond. We are breaking 3 mole of these hydrogen-hydrogen single covalent bond. So there's 3 times 4, 3, 6. We close the bracket because there's everything we need to break, and then minus everything we need to form. We have 2 times NH3. Now this is the confusing bit for a lot of students. 2 times NH3 means I will have 3 NH bond for 1 NH3, and then I have another NH3. So altogether I have 1, 2, 3, 4, 5, 6. So I am forming 6 times NH bond. So be very careful. NH bond is heterolytic between 2 different atoms. So we're looking at the different part of the data booklet. Not too sure how the new syllabus specification would give you in the question paper. Because if they print out the whole data booklet inside the question paper, it's going to be quite thick. So I guess they'll be very selective in terms of what data they will ask you. And it can probably restrict them, or probably not, in terms of the question they can ask you. All right, so 2256 minus 2340. Your calculator show you a negative, which is okay. But then, sometimes your enthalpy change is positive and you have to learn to interpret a positive enthalpy change with a sign, a value, and a unit for obvious reasons to get the full marks. The next thing, state the essential operating conditions. As you know, Haber process operates under three individual conditions, even from your IGCSE, GCSE or all-level days. So first one, you use finely divided ion catalyst. This is to increase the surface area of the heterogeneous catalyst, because this catalyst is in a solid phase, is a different phase, different state as your gaseous reactants. These are definitions stated in the as rate of reaction topic. Now in terms of temperature, so we have a temperature of around 400 to 500 degrees Celsius. Somewhere along that line is the generally accepted convention. We also need a high pressure of around 200 to 300 atmospheric pressure. Whether it's for exactly 200, 300, I'm not entirely sure, but I know it's not at 1 atmospheric pressure. It's a very high pressure, relatively high temperature, and then a finely divided ion catalyst there. As for the next question, there are 4 marks altogether. This is about the choices of temperature and pressure. So first of all, you need to think about temperature and then pressure. The choices always come down to 2 things, rate versus equilibrium. This rate versus equilibrium is always a very popular question. Of course, the question doesn't say rate versus equilibrium, but when I say that, what I mean is rate versus amount. Equilibrium refers to this equilibrium yield of the ammonia, which is your product. As a chemical engineer, your goal for your boss is to produce as much product at the lowest possible cost. This forward reaction is exothermic. You see, we talk about forward reaction being exothermic, means that it releases heat energy. So based on our calculations, the forward reaction to make ammonia, to form ammonia, is exothermic. So that means it releases heat energy. So high temperature, when you increase temperature, what would the equilibrium tries to do? High temperature means the equilibrium or the system will try to lower the temperature, will want to decrease temperature, but you only know how to release heat because that's what you do in the forward reaction, releasing heat energy. If you want to decrease temperature, do you want to release more heat or do you want to release less heat? Well, to get lower temperature, you will release less heat, and by releasing less heat, therefore the equilibrium will shift to the left, and when you shift to the left, you will have lower yield of ammonia. That is not good at a high temperature. So what can we do to counteract this? So do we want as low temperature as possible in order to go to high yield of ammonia? Of course not, because however, too low temperature will make the reaction very slow. So 400 to 500 degrees Celsius is the best compromise. So I've written quite a lot there. You can probably summarize it a little bit and get straight to the point. So now in terms of the pressure, so high pressure will mean greater collision frequency. It will mean the reacting particles, they are much closer together. And when they are closer together, they can collide more frequently. And when they collide more frequently, the rate of reaction will be faster. So faster rate of reaction due to the higher collision frequency. Last but not least, we must also talk about equilibrium yield as well in terms of pressure. Because of the compromise we make on the temperature, the high pressure there would shift the equilibrium to the side with lesser gaseous molecule. You have 1 and 3. You have 4 moles of gases on the left as reactants and 2 moles of gaseous reactants. 2 moles of gaseous products. So when you increase pressure, your equilibrium tries to decrease pressure. When you try to decrease pressure, it will go to the side with lesser gaseous molecules because you are doing Le Chatelier principle there. So what we can say is 4 moles of gaseous reactant. I think a lot of people, they forget that. They just say 4 moles on the left, 2 moles on the right. That is not correct because pressure affects gases the most. So 4 moles of gaseous reactants versus 2 moles of gaseous products. So at higher pressure, the equilibrium will shift to the side with lesser gaseous molecules. So 2 moles of gaseous products. Higher pressure, shift the equilibrium or shift the reaction to the side with lesser gaseous molecules, which means in this case it's going to favor to the right hand side. So therefore we get more yield of ammonia. So yield of ammonia will increase at higher pressure, the rate will be faster. But with temperature, because the flow reaction is exothermic, when you go too high of a temperature, the equilibrium will shift backward and that will give you a low yield of ammonia. So this, however, would also mean that the reaction will be very slow if you go lower temperature. So in the compromise, the best compromise between the rate, the low yield of ammonia, as well as the getting a fast enough rate, you come to this compromised temperature here. But that doesn't apply to pressure, because high pressure will both favor a faster reaction as well as a higher equilibrium yield of ammonia. Those are all the idea about rate and equilibrium for temperature as well as for pressure. This is a very famous essay. The 2 marks are for temperature, 2 marks are for the pressure, and that can be broken down into 1 for the rate and 1 for the equilibrium, or how much you get for the yield of the product. Now, one of the major uses of ammonia is used to make fertilizers, obviously, and fertilizers are used to improve plant growth. All those nitrogen, phosphorus, potassium, nutrients required by the plant. So now, what do you want? You want ammonia reacting with H3PO4, but very specific. You want to form diammonium hydrogen phosphate, which the formula has been given there. So you have ammonium and you have HPO4. If you can imagine H3PO4, when you lose a H plus, you're going to get H2PO4 minus. And then when you lose another H plus, you're going to have one H remaining and then PO4, 2 minus. And then when you lose another H plus, you will get the phosphate ion, PO4, 3 minus. So going back to this is the one with 2 minus charge, because there is 2 ammonium, which is 2 of that plus 1 charge. You will also produce, you won't produce water, because when ammonia acts as a base, it doesn't produce water because it balances out the atoms as this lone pair there, except the H plus. You accept one H plus, you become NH4 plus. You accept another H plus, you become another NH4 plus. So altogether, you just need 2 ammonia, and that equation should balance out. So 2 of the hydrogen goes there, become H plus, you get 2 of the ammonium. Now this becomes HPO4, 2 minus, and this should be alright. They don't ask for step symbols, we are okay for that 1 mark there. Now explain this reaction in terms of Brown-Stirred-Lowry theory for 2 marks. So we need to say what is a Brown-Stirred-Lowry acid and what is a Brown-Stirred-Lowry base. So Brown-Stirred-Lowry acid is a proton or a H plus donor, as stated in the syllabus. We can see that H3PO4 donates 2 protons, donates 2 H plus to become HPO4, 2 minus. So there's your first bit of the definition, and don't know why you choose that same color. The second bit, Brown-Stirred-Lowry base is a proton acceptor. So if you accept protons, that means it's a proton acceptor. I guess both things is the same thing. You could have said it accept proton, or you could have said it's a proton acceptor. It doesn't matter. I'm just trying to follow the same standard as I did in the previous question, really. No particular reasons. So the ammonia accepts protons. Each ammonia accepts 1 protons, okay, on its lone pair. On its lone pair of nitrogen to form ammonium ion. Okay, all right. Now part D. So the first question here really is all about eutrophication. So what we can say is eutrophication occurs. Eutrophication is a fixed essay you can prepare for. It's part of environmental chemistry, and it's basically this uncontrolled use of nitrate fertilizers, and they can get washed down into the river, especially during heavy rains, because all nitrates are soluble If you think about your solubility rules, all nitrates, salts are soluble in water. This includes all those fertilizer which contain nitrate. So I've just talked about eutrophication. There's no way you can get all the marks just by talking about one thing. You know the exam skills is all about contents. It's all about the points of interest. So for 3 marks, you need to have 3 points of interest. So if that's my first point, I need to describe what is eutrophication, because leading up to the severe reduction in water quality. So when that happened, then we get nitrate fertilizers will encourage. So when they get washed into the rivers, so when washed into river or lake, whichever one really, river or lakes, will result in severe growth or very rapid growth of algae or algae on the water surface. So they grow on the surface. So what happened then is this will block sunlight because they are blocking the sunlight to the water plants, to the aquatic plants or water plants which cannot photosynthesize. If they cannot photosynthesize, they cannot produce food. If they cannot produce food, they cannot produce oxygen. So therefore, the oxygen, the dissolved oxygen in the water, in river water, drops or decreases, and as a result of that, aquatic animals will die. Aquatic animals die, the ecosystem is destroyed. So basically, the river is kind of ruined, the water quality is quite bad, and then when the animals die, a bacteria will infest on them, and you get a growth of bacteria, obviously. Okay, so the ecosystem get destroyed, something like that. Alright, so it's all about the rapid bacterial growth afterward as well. So rapid bacterial growth, probably I don't say the ecosystem get destroyed, perhaps I can say bacterial growth, bacteria multiplies, bacteria grows as they feed on the dying animal. On the dead animal, not dying animals, on the dead animals, okay? So a lot of these points, you don't really need to follow word by word. It's basically essays which you need to know the order of events, and you can write in your own words, obviously. What next? Oxides of nitrogen are produced by the action of bacteria on nitrate fertilizer. Explain the problems, so there's plural there. And then release of oxide of nitrogen into the atmosphere. Include an equation, so you need to have at least one equation. So oxides of nitrogen into the atmosphere, this is about catalysis. This is about homogeneous catalysis in the upper atmosphere, where we have NO2 catalyze SO2 going to SO3. So they say something about an equation. So what we could say is NO2 plus SO3 plus SO2. The SO2 goes to SO3 in the industry as part of equilibrium process, and you need a catalyst and pressure and temperature. In the upper atmosphere, all of these are just gases. We don't put V2O5 in the upper atmosphere. Instead, the SO2 go to SO3, catalyzed by this NO2. So the NO2 get involved in the reaction. It give away the oxygen to the SO2. So the SO2 steals the oxygen. The SO2 get oxidized in forming the SO3. Having said that, the NO2 will get reduced because it has lost the oxygen. One of those cases, one of those really simple cases where you can use gaining and losing oxygen to think about what is happening there. Now this thing here, the NO, can be regenerated because a catalyst is not used up in a reaction. The catalyst is regenerated. Now what happened there? I know they say include an equation, but they don't say include the equation. So that means you can write more than one equation. These are the three general equations that go together, especially when you want to talk about the formation of acid rain as catalyzed by NO2. So this SO3 plus your rainwater is going to give you your acid rain, which is H2SO4. So having said that, what is the danger of this oxide of nitrogen? Well, we can see that the effect is that the oxides of nitrogen can catalyze the SO2 forming SO3, and the SO3 can cause acid rain, can form acid rain, and this acid rain that can destroy limestone buildings, that can destroy crops, they can destroy limestone buildings, they can destroy crops, limestone buildings, and obviously they can make river water really acidic as well and kill some river animals and stuff as well. So that's it really. The question is probably worth 1 mark. Talking about the effect in terms of the NO2 forming acid rain that is possible. There's another answer that's possible here. I've only talked about the homogeneous catalyst where the NO2 is in the same state as the gaseous SO2 when they catalyze this whole process. But of course, you could have gone for the other option where the NO2 form acid rain. So you could have gone for just one equation. The NO2 plus H2O, this is a disproportionation reaction. So this disproportionation reaction would actually form HNO3, but that is not the only product it will form, and you will not be able to balance this equation unless you know the other product as well. So this is nitrite ion, and this is nitrate ion, nitrogen plus 5, and nitrogen plus 3, oxidation state from the redox topic. This is nitrogen plus 4. Changes in oxidation number must be balanced using changes in oxidation number to balance chemical equations. So you need 2 of that, and since the +1 and -1 oxidation number changes get cancelled out, so 2 nitrogens, and I have 4 oxygens, and I have 5 oxygen. 4 plus 1 is 5 oxygen, 2 hydrogen there. This equation is going to be balanced like that, provided you know it's a disproportionation reaction. So you could have written down this equation, disproportionation reaction, and then obviously you can say that the oxide of nitrogen can form acid rain, and this acid rain can destroy crops and limestone buildings and whatnot. So this is NO2 catalyzing the SO2, giving SO3 that can go on to form acid rain. This is NO2 dissolving in the rainwater to give you the acid rain itself. Both of them could be accepted as the problem associated with this oxide of nitrogen to the atmosphere. In hindsight, this is probably more direct. I should probably have written this instead of this. There are some years where they say write a series of equations on how the NO2 can result in the formation of acid rain. Okay, so there should be cases when you need to use these, and there should be cases when you need to use these. In this particular question, either of which will be acceptable. We could probably have gone with this, which is a lot simpler. And that's it really for this 2-mark question, environmental chemistry there. And that concludes the 21 marks overall question there.